In this tutorial, we're going to look at air pressure or gas pressure. So let's start off about looking at what it actually is. Okay, if we imagine we've got some particles here, they're molecules or atoms or whatever. They are constantly moving randomly, and they do this because they've got energy. The more energy, the faster they move. Okay, so you've got all these particles, they're moving in random directions. Now, they don't always miss. They're constantly colliding with not only each other, but also other molecules as well. Not only with other molecules, but also with solid objects. So let's take an example. Say you've got a container, and say this is one of the inside faces of the container, and you've got gas inside at some pressure. And now these molecules are moving randomly, yes, but they will constantly collide with the walls of the container and each other. So those particles impacting with the walls of the container. Now, depending on the energy of the particles, they will have more energy. If they're, say, hotter, they'll have more energy, so they'll move faster, which means more collisions, and the collisions will have more momentum. But those particles constantly impacting with the side and each other cause pressure. Now, how do we measure this pressure? Well, the old method of measuring it was the PSI, or pounds per square inch. So what that means is if you've got a square of 1 inch, okay, so you've got 1 square inch, and whatever pressure exerts or what is measured per square inch. So you could have 5 pounds putting pressure on 1 square inch. At sea level, though, the pressure is 15 pounds per square inch. Now, 15 pounds is roughly 7 kilograms. So, 15 psi means, say, 7 kilogram weight is being exerted on a 1 square inch area. A more modern way of measuring pressure is bar. So 15 psi, or the pressure at sea level, is 1 bar, which equals 1000 millibars. And that's a more modern way of measuring pressure. The SI unit for pressure, though, is the Pascal, or PA for short. So 1 bar equals 1.0 times 10 to the 5 pascals. Okay, so i.e. the pressure above sea level is 10 to the 5 pascals. Okay. Now, how do we give the gas more pressure? Well, we need to do that to do that with a smaller container. Thus, the gaseous particles are closer together and you have more impacts. Another way is to heat the gas up. And what this does is it infers energy to the gas. So let's take the example of the box again. So we've got gas in a box. Let's just finish the box just to make it a bit clearer that we have got the gas contained in the box. Very bad drawing, I know, but it serves the purpose. Okay, so we've got a box here, and it contains all the gas. Just make it a bit neater. There you go. Okay, so we've got a box that contains gas. Say now we put a fire underneath it. Okay, the fire is giving out energy. We know that because we can feel it. We can feel it as heat. So the fire loses energy, minus energy. And these particles gain energy from the heat. So they get plus energy. All these particles get plus energy. And what that means is the particles move faster, so they've got more collisions, so they're more frequent, but also because they're moving faster, that increases their momentum, so they hit with a greater force, hence increasing the pressure. Now, if we take another example of the Earth, nice green Earth and blue, obviously, but we'll have blue for the atmosphere. So we all know if we stand on the Earth, our feet are firmly planted on. If we jump, we fall back down pretty quick. So gas is a lot lighter, it's got a lot less mass than us humans. So why doesn't it just settle on the surface in a thin layer? And the answer is actually pressure. At minus 273 degrees centigrade, or absolute zero, particles have got no energy. They don't move. And in that scenario, yes, the atmosphere would fall to the surface of the Earth because it would have no energy. It would have no way of being on of keeping itself stable. However, as soon as we put pressure into the equation, hence temperature, we've increased temperature. The average temperature is 15 degrees centigrade, which is very high compared to absolute zero. Then the particles have got a lot more energy and they're colliding with each other, which supports the atmosphere under its own weight. So you've got particles colliding with each other, so they bounce off, and that supports the atmosphere under its own weight. Thanks for watching. Please like, subscribe, and comment.